Howdy. Thank you guys for being here today. Hope y'all are all doing well. Um, Happy Tuesday. Um, Today, we are going to pick up where we left off last time. Last time we derived these point reactor kinetics equations, and today we're gonna talk more about them, understand their solutions, and how they can help us understand time-dependent problems. So, let us before I got started, any questions about the homework, current homework? Um, I wanted to let y'all know that for the current homework, I extended it. So like there was the thing where I had assigned it for a Thursday to be due the following Thursday. Um, and the issue with that, I guess the only issue with that really is that it doesn't give you time to get help for like that homework on a homework help session. So part of what I was going to do is I basically extended the homework that was supposed to be due Thursday of this week to Friday. That way, if you ended up with needing questions on that homework, then you can come to the help session and get help with what is due for um you can get help what's due on for the homework that's due on Thursday. And I'm sorry that I'm looking at my phone. My tablet where I have my like annotated notes is dead, so I was just pulling those up on my phone so I can make sure I'm not telling you guys anything wrong. All right. So if there are no homework questions, hopefully that's because it's going awesome and we understand everything perfectly. If it's because we haven't started yet, then we should probably get started soon. Like after today, we would probably be able to do most of that homework, if not all of it. So if we haven't started the current homework, that would probably be a good thing to do. That way, if you do end up with questions, we can get those addressed. Yes. Hmm. Wait, sorry, what was the question? Yes. Yes. So yeah, right. Okay. Yeah. The one with the AP 1000 and the unit cell and all of that. Yeah. So that is a problem on the current homework. So yeah, if you already did it on the previous one, yeah, exactly. Just resubmit for the current one. All righty. About the deadline extended? Yeah, I sent an email about that last week because that was a problem that was for like it was originally on homework 4, but now we're on homework 5. So it's a part of homework 5. Yeah, you would just turn it in onto homework 5. It wasn't if you turned it in on homework 4, it wasn't graded on homework 4, it was just skipped. So yeah, you just resubmit that one on homework 5. Okay. So, last time that we were here, we started talking more about time dependence, and the main like physics that we weren't including when we did time dependence before is that we weren't including the fact that there are neutrons that are born delayed. This is 10.
That both ones for this week out.
Yes. Right. So yeah, we're starting on 10 and then 11 is for tomorrow. So when you have a fission event, there's a nucleus that fissions, and like almost immediately after that fission event, you get some neutrons that come out of that reaction. Those are what we call the prompt neutrons. And those fission fragments, they are very unstable, they are radioactive, and they very quickly start decaying. As those fission fragments decay into fission products, these fission products, some of them will emit neutrons as they decay. So we talked about that last class. These fission products that decay and produce delayed neutrons, we call them delayed neutron precursors. And we basically said, well, if these delayed neutrons are being produced in our system, then if we have like our energy dependent diffusion equation, we can account for the production of those delayed neutrons with a delayed neutron source term. So that's this extra SDN right here. And this is just our energy dependent conservation equation. Every term is a energy dependent rate density. So every term has units of neutrons per unit volume, per unit time, and per unit energy. And basically what we did last time is we came up with a way to express that delayed neutron source term by introducing some definitions relating to these delayed neutron precursors. So there's a Ci, which is the density of so there's we have these delayed neutron precursors, and there's a lot of them in our reactor. In a reactor, there's like over 200 different delayed neutron precursors that have been identified. So what we usually do is we group these delayed neutron precursors together by ones that have similar half-lives and decay constants. And so Ci represents the density of some group of delayed neutron precursors. And it's a density, so it has units of like inverse volume. You can think of that as like particles per unit volume, but the particles are kind of like a fake unit, so you could also just write it as 1 over volume. The decay constant for these delayed neutron precursors, it means the same thing that we talked about when we did decay chains. It's a probability per unit time that something will undergo decay, specifically that our type I delayed neutron precursors will undergo decay. And then we can introduce a kind of like the equivalent of a fission spectrum, but for the neutrons that come out of delayed neutron precursors. So that's the chi sub I. And then if we kind of multiply all of those quantities together, we get something for each delayed neutron precursor group that kind of represents the number of neutrons per unit volume and per unit energy that are being emitted by that group. And if we have a bunch of groups in our reactor, then to get the total delayed neutron source term, we just sum up over every single group in our reactor. And so this was the delayed neutron source term, and then we saw that it depends on these precursor densities. So we also needed an equation for the densities, and to do that, we just used conservation. We said that the rate of change of those densities is going to be equal to the rate of their gains minus the rate of their losses. These precursors, they get born because of fission reactions. So their gain rate is like proportional to a fission reaction rate. And then they lose, delayed neutron precursors go away, get lost because they are unstable and they will decay. So we introduced a kind of like, this is kind of like nu F. It's the number of delayed neutrons that come out of each precursor of type I. And then we assume that each delayed neutron precursor of type I produces exactly 1 delayed neutron, so that this quantity is basically equivalent to the number of delayed neutrons that are emitted for each type I precursor group. So then the rate of change of our precursor density looks like a fission production term minus a decay rate. And so then, like, this is our energy dependent diffusion equation, but now we've spelled out the form of that delayed neutron precursor, the delayed neutron source term, and we also now have equations for each delayed neutron precursor concentration. So I represents the number of delayed neutron precursor groups. So this is a set of, we have one like diffusion equation, and then we have capital I, if capital I is the number of delayed neutron precursor groups, then we have capital I numbers of these density equations. We have one for every group. So what we did from there, we took all of that information, we used that equation as a starting point, and then we derived the point reactor kinetics equations. So these are just kind of like the steps that we went through to do that. We assumed that the medium was infinite, so we could get rid of the leakage term. We assumed that the medium was homogeneous, so that none of our properties depended on position. We integrated that energy-dependent diffusion equation over all energies. We recognized that some of the terms in those equations contain probability density functions, such that when we integrated them over all energies, they gave us a factor of 1, which allowed some things to simplify. We made use of a lot of prior definitions so that any like energy integrated densities, we recognize that as just the total density. And we also made use of the definition of an average of a function to take some of these complicated integrals and rewrite them as averages. Um, in doing that, we also introduced some definitions so that we could replace these like diffusion-esque terms with terms that are more like relating to the delayed neutron physics and the basically to convert our equations into the point reactor kinetics form, we introduced these definitions. So whenever we write this equation with the energy dependent diffusion equation with delayed neutrons, we should be familiar with this equation, just like we should have been familiar with it before we added the delayed neutron term, but now there's a new term, so we want to be familiar with that too, right? We want to know definitions for chi, definitions for lambda I, definitions for ci. We want to know what these terms mean, similar with all of these definitions that we used to derive the point reactor kinetics equations. We need to know what these symbols mean. We need to know what they like physically represent, and we need to know their units too if the quantities have units. So this is just kind of like a review slide to put all that information for you in one place. When we plugged in all of those definitions, we got these point reactor kinetics equations. Um, and so if we let capital I be the number of delayed neutron precursor groups, then we have capital I versions of this density, precursor density equation, and then we have one equation for the neutron density. And this sum is just a bunch of individual terms, but all of those terms are a part of the same equation, whereas the density term has a C sub I. So if I equals 1, you'll have an equation. If I equals 2, you'll have an equation. And for every value of I, you'll have a precursor density equation. So these are the equations that we can use to investigate how reactors behave as a function of time. Um, the name is kind of misleading when it says point kinetics. We don't treat the reactor as a point. We are effectively assuming that there's no spatial variation in the flux shape. Um, when we derived the point reactor kinetics equations, that was how we derived it in class by the steps that I just outlined. You don't have to assume that the medium is infinite to get these same point kinetics equations. And so one of your problems on the homework is redoing the point kinetics derivation, but without making the infinite medium assumption. And that is laid out all in the notes. And I think in the homework, I should have told you like what pages in the notes to look for that derivation. The whole point of doing that is to see that you can do the same approach to a more complicated like initial neutron distribution, and you're going to arrive at the same point reactor kinetics equations. Um, so each of these quantities that we introduced, they technically all will depend on the neutron, the energy dependent neutron density. But in a lot of cases, we can basically treat them as constants, and then we can do analytical calculations involving the point kinetics equations. So that's going to be our goal for today, is to basically understand what we can do with these equations and what they can tell us about time dependence of our neutron population. So if these are when we say that they're a coupled system, it means that these governing equations have two variables. Like if we were to solve for these equations, we'd be trying to solve for the neutron density. We'd be trying to solve for this n total. That's like one of our variables. And then we'd be trying to solve for all of these precursor densities. Um, and notice that the precursor density appears in my neutron density equation, and the neutron density appears in my precursor density equation. So these are a coupled set of equations because the variables that we're solving for appear in both of them. And so they are a coupled system of a certain number of equations. And we were just saying that if we have I delayed neutron precursor groups, then we have I number of the density equations, and then we have plus one. So we have I precursor density equations, and we have one neutron density equation. So these point reactor kinetics equations, they represent a coupled system of basically I plus one equations. And Um, to get here, we did introduce a bunch of these new terms like capital lambda and beta and stuff like that. So I did want to like revisit those real quick just to make sure we're all on the same page about what those definitions are. And then we can get into like actually solving these equations. So we introduced capital lambda, which is the mean generation time, and it basically tells you about essentially how long a neutron is alive in your reactor from when it's born to when it uh to when it causes a new fission, or until when it gets absorbed. Maybe it causes a fission, maybe it doesn't. And so if the mean generation time is the average time between two birth events in from one generation to another, then it is related to LP, which is the prompt neutron lifetime, and they're related through K effective. So because of this relationship between the prompt neutron lifetime and the mean generation time, and those relationships involving K effective, we can actually talk about the criticality state of our reactor in terms of how does LP, the prompt neutron lifetime, compared to the mean generation time. And so like we basically want to ask like if K effective is positive or negative or one, sorry, if it's greater than one, less than one, or equal to one, what's the ratio? How does the prompt neutron time compare to the mean generation time? So to see that, it's probably best to write this as a fraction. So like if we wanted to get K effective by itself, then what we would do is we would divide both sides by big lambda, right? So K effective would be the prompt neutron lifetime over capital, sorry, let me do a better capital lambda. So if we have a subcritical configuration, if K effective is less than one, which one of these is bigger? Is the prompt neutron lifetime bigger or is the mean generation time bigger if we have a subcritical system? Yeah, mean generation time is going to be bigger, right? In this configuration, the mean generation time is bigger than the prompt neutron lifetime if we have a subcritical configuration, because that means K is less than one, and that means that yeah, the denominator is bigger than the numerator, so that's what we get. Um, how about if it's critical? How about if K is equal to one? How does the LP and the big lambda compare? They're equal, right? They have to be the same. If K is one, then this ratio then these two are the same. So LP is equal to big lambda if we have a critical configuration. Sorry, I have a hard time drawing big lambda today. And then obviously if it's supercritical, that means that K effective is greater than one. So that means that the prompt neutron lifetime is going to be bigger than the mean generation time. So just like if I can tell you if my reactor's critical or subcritical or supercritical, how do the BMs and the BGs compare? You could also tell me about how the LP and the mean generation time compare too. Um, and so I think hopefully that we can think about that intuitively, that if we're talking about the lifetime of a prompt neutron versus the lifetime from the average time for a neutron to go from birth to death in two successive generations, that if your prompt neutron time is shorter than the generation time, which is like how long it takes for you to reproduce yourself, then you can't sustain a critical reaction. You have to have LP equal to the mean generation time or LP greater than the mean generation time. So that's just some more stuff to know about the relationship and the definition of the mean generation time. Another thing that we introduced is the definition of reactivity. And so it's an unfortunate thing where we use the same symbols for a lot of different things. If you see rho in nuclear engineering, it could be a mass density, like kilograms per meter cubed, or it could be reactivity. Most of the time, if you see a mass density, it's because you're doing like an atom density calculation, and that's where the mass density would appear. Sorry that we have to use the same symbols for multiple stuff. If you see a rho in like any other context, it probably represents reactivity. And so this is how we can define, this is how reactivity is defined. It's defined as your deviation of the multiplication factor from its critical state. So what it means is that well, we can see what it means if we consider what would rho be if our system was subcritical or critical or supercritical. So if our system is subcritical, if K effective is less than 1, then what does that mean about rho? Is rho positive or negative or 0 if the system is subcritical? It's going to be negative, right? Rho has to be negative if k is less than 1, right? Because if k is less than 1, check it out. If k is less than 1, then here we're going to have a number less than 1, like maybe we have like 0.9. And so we're going to have 0.9 minus 1, and 0.9 minus 1 is a negative number. So we're going to have a negative number over a positive number, which means the quantity, which is rho, has to be negative. What if k is equal to 1? Then what does rho have to be? It has to be 0, right? So if a reactor is critical, it means K effective is 1, but by definition, it also means rho is equal to 0. So that's why we say reactivity or rho, it's how far you deviate from critical. And so if you are exactly critical, rho is 0 because you're there. And if you are below critical, then your rho will be less than 0. And if you are above critical, if you're supercritical, then what this tells us is that rho has to be positive, right? The reactivity is going to be positive if we have a supercritical configuration. Because that means k is going to be greater than 1, right? So now instead of this being 0.9, maybe it's like 1.1. And then I've got 1.1 minus 1, which is a positive number, over another positive number, which gives me a positive. Um, so when we talk about these, I guess, kind of better understanding the Dr. Svetkov notes terminology, he uses some extra subscripts that I don't, or superscripts that I don't always use because it's sometimes inconvenient to write them. So with all of the indexes that you'll see in this section, there's an index I, which is for the number of delayed neutron precursor groups, and we already talked about that. G is the index for the energy group, and that's another thing that we've already seen and we've discussed. But there's a new index that you'll see, which is J, and that's for the number of fissionable or yeah, basically the number of nuclides that can fission in your fuel or in your system. For a lot of problems, we know what fuel type we have. Like if it's a PWR, we know that it's a uranium fuel type, and so J would basically just be 1, and we would just use the values for that like fuel type. So I think the J index complicates things more than is necessary, so I usually don't write things with the J index. But if you see the J index, it's just telling you that these are quantities for a specific fissionable nuclide. So that's what this table is basically showing you is the number of delayed neutrons that are being produced. So the FD is the number of delayed neutrons for a type J nuclide. This is the total, nu F is the total number of neutrons per fission for a type J nuclide, and then beta is the delayed neutron fraction for a type J nuclide. Um, Question.
So why would J be important? Like a fast reactor or something?
It's mostly important if you had to do more detailed. It basically just depends on your fuel type. I guess you could also say that it kind of depends on like where is your fuel in its because like when we start with fresh fuel, it's all uranium, but as the fuel fissions, uranium 238 will like absorb neutrons. Some of those and eventually uranium 230 yeah, uranium-238 can become plutonium. And so like your fuel composition will kind of change over time. So that's part of it is like where are you in like the life cycle of your fuel? Yeah. And so beta, that's defined as the delayed neutron fraction. So like if I wanted to get the beta values in this table and I have the number of delayed neutrons that are coming out per fission and I have the total number of neutrons that are coming out per fission, how would what would I do with these two nus to get the delayed neutron fraction? Because the delayed neutron fraction is it's the fraction of neutrons that are born delayed, right? So it's the delayed neutrons over the total. And so if I have a production of delayed neutrons and I have a production of total neutrons, if I take the ratio of those two, that is going to give me the delayed neutron fraction. So if I do nu for my delayed neutrons of type from fuel from type J, divided by nu for all of my neutrons that are emitted from a nuclide of type J, that is how you get these beta values in that table. It's just from the definition of the delayed neutron fraction. Okay. So yeah, this is a useful table. If you're told what kind of fuel you have, then you can go here and you can see what your values of beta are. And also notice that these quantities are energy dependent. So like what the value for beta is going to change depending on if you're talking about neutrons coming out of thermal fission or fast fission. But yeah, that's a useful table to be aware of. So like we were saying, we have all these different precursors in our fuel. Um, even though we have so many of them, we don't have to keep track of all 270 of them. There's only like a couple dozen that are significant for engineering applications, and it's mostly based on like how how long are the half-lives and the decay constants relative to like the time that we care about analyzing our reactor. In terms of our reactor, do y'all think that we're going to care mostly about delayed neutron precursors that have small half-lives or large half-lives? And why would we care about the small ones more than the large? They decay faster, right? So exactly. So we only care about the ones that are with half-lives that are small, because they will decay faster. And basically, when we say small, it's like on the order of seconds to minutes. Some of these delayed neutron precursors, they're going to have crazy long half-lives of like hours or days or years. And those are emitting neutrons so slow that like we can basically ignore them from our calculations. But the ones that have short half-lives and decay fast, we have to consider those mostly. Um, so basically what that means is that we can ignore the ones that are way out of that range, and we can group the ones that have similar decay constants and half-lives together. So that's where the idea of delayed neutron precursor groups comes from. And the most common form, the most common grouping is to do 6 delayed neutron precursor groups. So 6 delayed neutron precursor groups is the most common. Like that's the most sophisticated that we'll do in this class. Obviously, if you do more groups, you will get like a more sophisticated, more accurate answer, but 6 is pretty sufficient for most calculations that we'll need to do. And so if we have 6 delayed neutron precursor groups, that means that capital I in our summations is 6. Um, And then each group of delayed neutron precursors has its own group decay constant and its own relative abundance. And the decay constant, do y'all remember how the decay constant relates to the half-life? That formula we derived on like homework 1? Yeah. Uh-huh. Perfect. Yes, it's ln of 2 over the half-life. So we'll say T1/2 of our I nuclei of our sorry of our I delayed neutron precursor group for a fuel of type J. Um, So same definition, it's just that the T one half looks a little bit more complicated because we're talking about the decay constant for delayed neutron precursor group I associated with fuel type J. And so that's lambda I, and AI, not artificial intelligence, but a subscript I is the relative group abundance, and it's just defined as the delayed neutron fraction for your group divided by the total delayed neutron fraction for all of the and so the total delayed neutron fraction means that you're just summing up all of your beta i's for every group. Okay. Yes.
How big is it?
I don't think it's going to change very much. And I think that's why, like, to exactly quantify it, I couldn't tell you. But people have done 6, they've done 12, they've done like everything in between and more. And I think they use 6 as a good cutoff because it gives you results that are like relatively accurate without having to like do a lot of extra computations. But yeah, in terms of quantifying that exactly, I do not know. Um, So so this is a table of what all of those group parameters look like for a 6 delayed neutron precursor group. So this is for every group I equals 1, 2, 3, 4, 5, and 6. These are the values of your AIs, your abundances, and your decay constants. And notice that we have them for different fuel types, right? So if it's 235 or plutonium 241 or plutonium 242, then we have different fuel, and therefore we have different lambdas and abundances. And if we have like a 6 delayed neutron group or a multi-group model, we can lump everything together as one effective delayed neutron precursor group using these equations right here. So it's basically just a way of summing up and like kind of taking averages effectively of your overall group values over the values in your group to get like an overall averaged or effective group one group constants. Um, so yeah, that's a useful one. You'll use this equation anytime you're assuming one effective delayed neutron precursor group, and that means that instead of having like a big sum, you'll just sum up all of these things in advance, and then you'll be working with like an effective value for beta and like an effective value for the lambda for that fuel. Um, so when we talk about time dependence, there's like two kind of characteristic problems that we want to study, and those types of problems are kinetics problems and dynamics problems. And when we talk about kinetics, that's basically what the point kinetics equations do for us. They basically give us a way that we can model the time dependence of our neutron population. So if you're doing kinetics, that is what allows you to model the time dependence of a neutron population. And like again, that's when we say point reactor kinetics, that is what these equations are doing for us. If we were to solve them, we would get that neutron density as a function of time, and then we could say how that time, how the density evolves as a function of time. Um, and so that's kinetics. Dynamics is kinetics plus some extra complicating features. And those basically have to do with the fact that anytime your system is changing with time, characteristics of that system can change too. Like for example, if we remove a control rod from our reactor, then what that's going to do is it's going to reduce absorption and it's going to allow our neutron population to increase. And as our neutron population increases, that's going to affect other features of our system. Like if we have more fissions, it's going to mean more heat is produced. That means that things in our reactor are going to heat up. As things heat up, certain parameters change, like our cross sections will change, our materials will expand. So if you have, those are feedback effects basically, and that's what dynamics is. It includes things like temperature and feedback effects. So we want to understand not just how a system responds right when you have some change, but also how does that change affect other parts of our system. And so we can think of our reactor as like a system that has a bunch of components that are all connected and that interface with each other. We use equations to solve and predict and understand aspects of our system. And we can solve them hopefully, and then we can understand how our system works. Like if we were to solve the energy dependent diffusion equation, what is that gonna, what piece of information, what solution would we get from the energy dependent diffusion equation? Yeah, right. And specifically, it's going to give us that energy dependent flux. So it can tell us about the flux as a position of, as a function of position, as a function of energy, and a function of time. So if you know, let me just erase that little scribble right there so it doesn't look like a Y. So if you know the energy dependent flux, you can compute the reaction rates at any point in your reactor. Also, if y'all are taking heat transfer and y'all are solving the heat diffusion equation, when you solve that, what's the variable that you get out of solving the heat diffusion equation? That heat diffusion equation, it's like a differential equation in terms of temperature. And so what the heat diffusion equation can give you is it can give you your temperature distribution as a function of position and a function of time. So like if we were to think about our reactor core, that heat, that temperature profile is going to look very different, like in the fuel compared to in the coolant, for example. And the heat, so that's a different class, but it's an important thing to recognize that these things are connected, and your temperature is going to affect your diffusion, just like your diffusion is going to affect your temperature. As things fission, they'll heat up. As things heat up, it affects your cross sections, which can go back and affect your flux. So this is an example of other quantities that are coupled in our reactor. The flux and the temperature are coupled, for the reasons that we've been talking about. So hopefully that is like intuitive, makes sense that these quantities affect each other, that if we make some change to our system, it can affect other things. And that's stuff that we want to keep in mind, especially when we're talking about doing reactor dynamics. So when we do these kinetics calculations, usually what we're assuming is that the system is initially critical, like before we do something to it. And then we want to see how does the system change if it's running critically and there's some change to the system, how does our system react to that change? Um, so if our reactor is initially critical, we know that that means that all of like the production and loss rates of our neutron population is balanced. And that means that the system is in steady state. Can a reactor be in that kind of configuration forever? Can it stay critical forever? No, right? And what are some reasons that the reactor might change from a critical state? Like, why can't it just be critical forever? Perfect. Okay, yeah. So like we're gonna get so perfect. You're as the fuel fissions, you get the buildup of fission products. And some of those fission products are highly absorbing. They change the cross sections of our fuel, and that will affect our multiplication factor. The fuel also is not an infinite resource, right? Like if you've got a certain number of uranium 235 in your reactor, you've got like say 5% uranium 235 in your reactor, and you turn the reactor on, those uranium 235 atoms are fissioning and they're disappearing. So like if you were to just leave that reactor, it's eventually going to go subcritical because fission products are going to build up, but also because the fuel itself is going to get depleted. So we can also talk about fuel depletion. And we could talk about a lot of other things too. There's a lot of things that can happen to our system that could make it deviate from its critical state. Um, so if we're critical and then we have a deviation of our system that takes us away from critical, what are the only two possible configurations our reactor can go into if it's critical and then it deviates from that? Subcritical or critical, right? If it's at k equals 1 and it has a deviation, it could either go above 1, it could have a kick up into being supercritical, or it could lose some and it can have a kick down into being subcritical. So it can only either go supercritical or subcritical. And when you have some change that affects your system, we sometimes refer to those changes as transients. So if you've ever heard that word, that's kind of like what we're talking about. You have some external event that acts on your system that changes the way that your system behaves. And so we want to understand what kinds of changes could happen. We want to understand how those changes are going to influence our reactor. And because we're interested in time dependence, we have to also be a little bit aware about over what time scales do these different changes take place. Because if you do something to change your system, there's going to be some aspects of your system that are going to respond almost instantly, and you're going to have other aspects of your system that have a slower response time. So we want to know both what changes take place and also like the time scales over which those changes occur. That way we can make sure that we're designing reactors that are safe in any possible scenarios that we could imagine. So this is talking more about different kinds of things that could change our reactor state. We already talked about like fuel depletion or fuel burnup, right? As the fuel gets used, the fuel is going to be consumed. That would generally reduce the reactivity of your fuel, but also some parts of our fuel, like if we have 238, it will absorb neutrons and will become plutonium that can fission. So your fuel can also produce new fissile nuclides, which could make like the reactivity of the fuel possibly increase. Um, but basically, all these fuel compositions, the fuel composition changes. That means that the reactivity changes too. We're going to talk a lot more about fission products in a couple days. Like after exam 2, that's what we'll move into. So we don't have to know anything more detailed than fission products, other than the fact that some of these fission products that are born are called, they're very highly neutron absorbing. They're called neutron poisons, and those can significantly change the absorption of our system. Temperature is a big one because usually if like we have a change in our reactivity, that means that we have a change in the fission rate, and that means that we're going to have a change in like the energy either being deposited into our reactor, and that means that we're going to have changes in temperature of our reactor. And if temperature changes, it can affect a lot of things. It can affect our material properties because of thermal expansion and contraction. It can also affect our cross sections because of things like Doppler broadening that we've talked about before, and we'll revisit those things because they're becoming more relevant as we get into our discussion about transients and feedback. Um, System changes, like you can, if your reactor is a system, you can insert absorbing control rods into that system, and that's going to change the properties of your system. Um, our systems also interact with the environment. Like most nuclear power plants have a heat sink that is somehow connected to the environment. Maybe they have cooling towers that are depositing that heat into the atmosphere. Maybe they're built on like a lake or a river so that they're depositing some of their waste heat into that stream. And so the South Texas project is the power plant in Bay City. Their secondary island where they have all the turbines and stuff, it's completely in open air. And so that means that sometimes you can have that system is coupled to the environment. And if the temperature outside gets too hot, or if that temperature outside gets too cold, that's going to influence how that plant operates, and they're going to have to shut it down, just like they did in the 2021 winter storm. Because that conventional island is outside, and in 2021 it was like below freezing for a really long time, these massive pipes that are usually pumping like many, many gallons per minute of water just froze solid. And so the environment affected our system, and our system had to respond by shutting the reactor down so that we could, be safe. And any other accident like a Fukushima or like a Chernobyl, some kind of that I guess Fukushima is kind of like environmental too. But any accident could be an unforeseen event that changes our properties and changes our reactor multiplication. Whoops. And so the other thing we were talking about is like classifying time and the time over which these changes take place. Generally, we kind of have three different time scales that we can talk about: the short, the intermediate, and then the long. When we talk about short time problems, the main thing that's going to influence the main thing that's going to happen in short times is like basically temperature responses. Like if your fission rate changes, if your fission rate increases, the fuel is going to be like the first thing that responds to that. The fuel is going to heat up first, and that's going to happen very, very quickly. So anything that could act on the system in a short amount of time is a short time problem. Um, in a short time problem, you can assume that in that first like minute or two, that your flux doesn't change very much. And then with time, and then you can use the point reactor kinetics equations to predict your behavior in that first like couple of seconds to minutes. The intermediate time problems, so like we're talking about hours to days, that's going to be more influenced by the buildup of fission products, things that add absorption to our system. That's gonna be the main thing that influences our intermediate time problems. And if we ignore the buildup of fission products, then the point reactor kinetics equations can still be relatively accurate, even if we're talking about like a few hours into a transient. But if we talk about anything longer than like hours, then it's the depletion of our fuel and the buildup of those fission products that's mostly changing our system. And so to do any kind of like long-term depletion calculations, you basically have to like have detailed knowledge of what your fuel started with, what was the flux in your reactor at every point, so that you can know how your fuel is changing as a function of time, and that can allow you to predict how that fuel is going to change over time, over long periods of time. So those are like the classifying of time problems that we should be aware of when we're thinking about transients and how long over how much time will these like changes influence our system. So if we return back to our kinetics equations, then hopefully now we've seen these, we've talked about some of those terms, and hopefully we're feeling a little bit more, confident with what with what these terms in our equations mean, and we have some concept understanding of like what these are hopefully going to be able to do for us. We are going to start to solve them, and we're going to make some assumptions. We're going to assume that our system is initially critical. We're going to assume that all of these quantities are constants. And we're going to assume that this reactivity is a step reactivity insertion, which means that our system is initially critical. So at time zero, the reactivity is zero because we're critical. And then at time zero, there's going to be some change to our system that's going to change the reactivity of the system. It's either going to cause a reactivity insertion of like an insertion of positive reactivity, which would kick our system into a supercritical state, or it's going to cause an insertion of negative reactivity, which would kick our reactor into a subcritical state. And we're going to ignore neutron sources. That means that this source term goes to zero if we ignore sources. Um, and if we make these assumptions, then the point reactor kinetics equations, they constitute a set of I plus one coupled ordinary differential equations with constant coefficients. They're coupled because they contain that number density and the precursor densities. There's I plus one of them because we have capital I precursor density terms, precursor density equations, and one neutron density equation. They're ordinary differential equations because they only contain the variable t, one variable, and they have constant coefficients because we're assuming that all of those coefficients, like the betas and the lambdas, are all constants. Um, so if the reactor, we're saying that the reactor is initially critical, so what does that mean about any rate of change terms at time zero? If the reactor is critical at time zero, what does that mean about the rate of change terms at time zero? Um, if they were equal to one, that would mean that there would be some change in the population. But if it's critical, that means the population doesn't change with time, right? So that means that the dn by dt terms all have to go to zero, right? Um, so so if we assume that the reactor is initially critical, that means that these time derivatives are zero. And this is specifically at t equals zero. At, right? Those derivatives are zero if the reactor is critical, which is just at time zero. And then right after time zero, we do some reactivity insertion, which makes our system go away from critical. So if we assume that we know that this is the initial density, if the initial density is just some known number, then we can show, and you're going to show this in homework 6, you're going to show it by setting this derivative equal to zero, plugging in time zero into both of these equations so that this says in total at zero, which we know is in naught, and that this says ci at zero, which is like the thing that we're trying to solve for. And if you do that and you use that definition of the derivative being zero at time zero, you should be able to solve that second equation to get this form for the precursor densities at time zero. And if you know the initial values of these two functions, then you basically have everything that we need to be able to solve the problem. So at that point, this is our complete problem setup. And so I've rewritten those equations. Well, I guess, yeah, these are our equations. This is the initial condition for the neutron density. This is the initial condition for the precursor density. And now we have a coupled set of I plus 1 equations. If we solve these equations, then we can find in total C1, C2, C3, all the way up to C capital I. So that's the goal. And let's see how we can get there. Um, so do y'all recall seeing these kinds of problems in like linear algebra or differential equations where you've got coupled sets of ordinary differential equations with constant coefficients? Because if you've when you see these and you see them over and over and over again, you eventually see them and you just recognize that the solution has like a certain form. And in this case, it's a sum of I plus 1 exponentials. So it's a sum of I plus 1 exponentials. So we basically have like a bunch of exponentials that evolve with time. Um, and each of these exponentials has it's like an e to some constant times time, and those things that are that are multiplying by time are called time constants, and all of the time constants for every solution are going to be the same. So these solutions are the same. The time constants for these solutions are the same time constants in the other functions. So they all have a similar functional form. It's a sum of I plus 1 exponentials. And each solution, even though the coefficients in front of those exponentials might be different, the time constants inside of the exponentials are the same. So like the way that we would write this is that we have a sum. So we're summing up, and I'm going to use the index k for my sum. We're summing from k equals 0 to capital I. For the in total, we have a coefficient up front, which is ak, and then we have e to the omega, which is the time constant, k, omega k times t, where omega k is that time constant. So this is what it looks like for the total for the total density. And for the precursor density, it is also a sum over k. K goes from 0 to capital I. And here, the coefficients up front are called bk, but for every I delayed neutron precursor group, we're going to have a different coefficient up front for this bk, but the exponential part is going to be the same. It's going to look like e to the omega k times the time. And so I've introduced an index k here. This k is not the multiplication factor. And notice that k goes from 0 up to I, so that in total, if we were to write this out, there would be I plus 1 terms in the sum. You would have a k0, k1, k2, k3, all the way up to k capital I. So overall, you would have I plus 1 terms in each exponential. And when we talk about the time constants, that's what the omega k is. The omega k is the time constant. And an exponential, what do the units of an exponential have to come out to? Exponentials are unitless, right? And so that means that the arguments that go into the exponential have to be unitless as well. So if time, t, has units of seconds, what do the units of the time constant have to be? Inverse seconds, right? So the time constant is going to have units of seconds to the minus 1. So our goal is going to be to find those time constants. Because then if we can find those time constants, we'll basically know what the functional form of our solutions are, provided that we have like an initial condition that we could use to find these coefficients up front. So we have the initial condition, we could find those coefficients, and if we could find the AK and the BK, and then if we could find the time constants, we would know how our function, both the density, the neutron density and the precursor densities evolve with time. Okay. Oh, question? Yeah. So the in total, there's only one in total equation. So there's only one constant that we need for the in total equation. No, you're good. That's an important point to raise, that we have I numbers of these equations, little I numbers of these equations, and then we have I plus 1 terms in each sum. So this would look, there would be a lot of terms here because you have to kind of have every I and you're summing over all of the k indices. So it is helpful to recognize that if you were to write these equations out, like if you were to actually start spelling out every single term in your equations, you would get a matrix. So the left side is just the derivative of my density, or the derivative of my precursor density. So like this is the left side, it's just a d by dt of this column of solutions. What we have right here, this first entry is my n of t equation. And really I should go over here. So notice this rho minus beta over big lambda, that is a multiple on n total, and that's this first coefficient right up here, which is being multiplied by n total. And then in this first equation, I would have a lambda 1 times a C1 plus a lambda 2 times a C2 plus a lambda 3 times a C3, and I would have I numbers of these terms. So I'd have a lambda 1 times a C1 plus a lambda 2 times a C2 plus a lambda 3 times a C3, and I would go all the way up to lambda I times Ci. So that first equation is just my density. the neutron density, and then my second and third and I equations, the next I equations down, those all come from this guy right here, where the first one is I equals little one. So I have C1 here, B, uh, I have a beta 1 times a lambda, and then that is multiplied by n total, which is the first entry. And then every other term is a lambda uh, for that group I times the density for that group I. And for the first equation, I equals 1. So I would have a negative lambda 1 times my C1. And then all of the other entries are 0 because for the density equations, you only evaluate it at one value of I. So this would be the equation for I equals 1. This would be the equation for I equals 2. That's the equation for I equals 3. That final one is the equation for I equals capital I. So like hopefully that helps us just to see how we could write these equations in a matrix form. Um, and um, from there, we've already said that our solutions are going to have a functional form that looks like a sum of exponentials. And we already know that those omegas are going to be the same for my N of t solution and for my CI solution. It's going to be the same exponentials. It's the same omega k that appears in both equations. So my general solutions are just going to look like e to the omega t. And our original equation had like a derivative of N of t and a derivative of the constant of CI of t. So I want to use this functional form and start taking derivatives and then plug those into my point reactor kinetics equations. So if my n total, if I have n of t that looks like e to the omega t, then what is dn dt? How would I take the derivative of e to the omega t with respect to time? Yeah, perfect. The derivative of an exponential, you get it returns itself, and then you also take the derivative of the inside. The derivative of the inside with respect to time is just omega. So you pick up a factor of omega, and then you get the original function. So notice omega times e to the omega t, that's the same thing as just omega times n of t, right? Because e to the omega t was my original function. And if I took a derivative of CI with respect to time, CI is going to have the same functional form. So the derivative of CI is also going to look the same. It's just going to be multiplied by CI. So the derivative of this is going to be omega times CI of t. And what we're going to do from there is we're going to plug these definitions into our point reactor kinetics equations, right? This is being plugged in here for the dn dt term. This is being plugged in here for the dci dt term. And doing that is nice because now we don't have any derivatives in our equations, and now these effectively just become like linear algebraic equations where we have unknowns that are just linear functions. In total is a linear function, and all of my CIs are also linear functions because all of the coefficients in these equations are constant. So if I move all my terms to one side, I can, it's a linear system. I can move all of my terms to one side, and I can basically group it so that everything that's a multiple on my n total is grouped here, and everything else is baked into this sum. So all I've done to get here is algebra, and then I'm recognizing that this is also a system that I can write as a matrix, where everything on the right-hand side is 0, and then in this first equation, I've got this big constant multiplying by n total. So notice that that's the first entry in this matrix. This is that constant times the value for n total. And then what I have in the rest of that first line is just all of my lambda i's times my ci terms. So I have a lambda 1 times my c1, lambda 2 times my c2, and etc. And basically, this ends up looking very similar to what we had before, but now this omega term appears along the diagonal. The omega, which is the time constant that we're trying to solve for, is along this main diagonal. And if this is a linear system and I have constant coefficients, then from our studies in linear algebra, we hopefully recognize that for our system to have non-trivial solutions, for our system to give us solutions that aren't just a bunch of zeros, what has to be true about this if this thing is like called a coefficient matrix, what has to be true about this coefficient matrix for us to get non-trivial solutions? Yeah, perfect. So that's we want to recognize that this is that kind of problem, and then we want to say that if we were to take the determinant of this coefficient matrix, then we get zero. So that's the next thing that we want to say. It's going to have non-trivial matrix if the determinant of the coefficient matrix is equal to zero. So, um, depending on the number of precursor groups that you have, that determinant is going to look worse and worse, right? Because like lambda I is based on the number of precursor groups. So if I have like 100 precursor groups, then I've got like 100 by 100 matrix that I'm having to like take the determinant of, which would probably just go to a computer if it's that bad. But so in general, what we're going to do is we're going to take the determinant of that matrix, we're going to set it equal to zero, and that's how we can find what these omegas have to be. And if the number is greater than two, then we kind of are going to have a really hard time solving this analytically. But if it's less than two, we can do some analytical calculations involving with these determinants. And I think I gave y'all a homework problem that does that. Um, and but otherwise, we basically have to solve this numerically. So, like, the more complicated problem is when you have like six delayed neutron precursor groups, and then we want to solve that problem, and we're going to have to do it numerically. So I wanted to kind of talk about how we would do that. Um, if you have like two groups, it's very straightforward, and you just get a nice analytical expression for omega. Otherwise, we have to solve it numerically. Um, so generally, this is how you would find those time constants, is that the approach from where we're at right now, where we have this linear system of equations, is that you're going to take, so if this is equation one and this is equation two, you're going to take equation two and you're going to get CI by itself. You're going to get CI as a function of like all these other things, including the total density. And then you're going to take that CI and you're going to plug it into equation one here for CI. So when you do that, that should eliminate the density, the precursor density from equation one. Because we're looking for non-trivial solutions, we can then take that equation one and just divide both sides by the by the neutron density. If we want non-trivial solutions, that means the solution isn't zero, so it's okay to divide by n of t. And then once you do that, you're going to want to solve the equation that you get for rho naught. You're also going to want to use this definition to rewrite the sum of all of your beta i's in terms of like an effective um, delayed neutron fraction. And then from there, once you invoke that definition, it's just algebra to get into the form that we want. And that form looks like this. Basically, we're trying to get an expression for this reactivity insertion. And it's going to look like, the insertion is going to look like omega times my mean generation time plus a sum. This sum goes from I equals 1 to big I, and we are summing omega times the delayed neutron fraction for group I divided by omega plus the decay constant for group I. I gave y'all a homework problem that is relate. Actually, I think I gave y'all this derivation on the homework. And this is also a possible exam question showing how you can get to this equation right here. I promise it's not that bad. These really are all the steps that you need, and the steps are shown in full on Dr. Svedkov's notes. So that would be a good one to know because whenever I'm thinking about possible exam like derivation questions, this is one that I could give you. Um, and so that's the equation that we want to get. But what I'm going to show you guys is this is also the equation that we can solve to find our time constants. So that was what I wanted us to see next is how we can take this equation and solve for what our time constants are going to be. So that equation is called the n-hour equation. The n-hour equation. It's valid for any number of delayed neutron precursor groups. And it is we can solve it to get the I+1 values of our, so when you solve this equation, there's going to be I+1 omegas that satisfy the equation. So when you plot this, it's going to look like this crazy thing with like a bunch of like a bunch of almost looks like hyperbolic tangent kind of functions. And there's going to be I+1 places where that equation is satisfied. Those intersections are going to correspond to the roots of this equation or the time constants that we're looking for. Just recall that all of these, the solutions that we're looking for are exponentials with these time constants. And we already said that these time constants have units of inverse seconds. Um, so uh, because all of our solutions are exponentials of these time constants, the sign SIGN of those time constants is important. Because if the sign is positive, like if omega k is a positive number, that means that our functions are going to increase exponentially with time. If the omegas are negative, that means our system is going to decrease exponentially with time. And if the omega is zero, then we're going to have e to the zero, which is a constant, and then our system is going to grow constant with time. The reason that they call this the n-hour equation is because you use it to solve for the time constants, and in the olden days, these time constants were in units of inverse hours, so that's why it's called the n-hour equation. But so ultimately, what we want to do is be able to solve this for those time constants. So what you're going to do in principle is you're going to plot this equation as a function of omega. So this right here, this is the, like, if you look at that equation as a right-hand side and a left-hand side, this is the right-hand side. And so you would be plotting this as a function of omega. So on the y-axis, you're plotting this function. On the x-axis, you're plotting omega as like a variable. And the reactivity insertion corresponds to constant lines in this problem. So we have two reactivity insertions shown on this problem in this plot. That red line is the positive reactivity insertion. Because okay, so notice this is the vertical axis. This is the origin of my vertical axis. So any y values or any reactivities above that are positive reactivity insertions. And then this line down here, this line is below the horizontal axis. It corresponds to negative reactivity insertions. So if you were to plot what's in the blue, the right-hand side, that's going to give you all of these curves. And I'm not going to like draw too much on this graph because I don't want to get it, horribly cluttered, but that's what all of these blue, what I'm showing in blue, that's what these are. These are just plotting this function as a function of omega. And so notice from the graph that we basically, if this is plotted with 6 delayed neutron precursor groups. So if I is 6, that means that I plus 1 equals 7, and I plus 1 equals 7. 7 should be the number of time constants that we can find on this graph. Um, So notice that if we look at these time constants, they are where the blue curves are intersecting the red curves. So if we have a positive reactivity insertion, if our reactivity insertion is positive, then these are the intersecting points between our in-hour equation and the constant reactivity insertion. So notice that there's 7 intersection points because we have I plus 1 time constants. And notice that these first 6 of them, or the first I of them, notice that these are all negative, right? Omega 6, omega 5, 4, 3, 2, and 1. These are all the omegas are negative because that corresponds to the y value, or sorry, corresponds to the x values of these points, and the x values of all of these points are to the left of the origin, right? So I of these points are negative. I of these time constants are negative. And notice that on this graph, the vertical asymptotes correspond to the lambdas for each delayed neutron precursor group. So this vertical asymptote corresponds to lambda 1, then we have lambda 2, lambda 3, lambda 4, all the way up to lambda 6. So notice that all of these time constants, the ones that are negative, they're all negative, and they're also less than lambda 1. They're all negative, and they are less than lambda 1, which is what we call lambda min. Because lambda 1 is the smallest of all of my time constants. It's like the algebraically smallest time constant. So notice I of them are negative and less than that minimum lambda. And then we have this other one over here, omega 0. And this time constant is positive. So the other one is positive, and also notice that omega, this last time constant was positive when the reactivity was positive, but it was also negative when the reactivity insertion was negative. And this time constant is also 0 if the reactivity insertion is 0. So the other time constant, omega naught, has the same sign as the reactivity insertion, has the same sign as as the reactivity insertion rho naught. And notice that when rho was 0, if we're at the if we're along the x-axis where rho is 0, then omega naught, the 0 time constant, the the time constant with the subscript 0 is 0. Um, and then if the reactivity insertion was negative, that's corresponding to this curve down here, then the omega naught is negative, right? Omega naught is always going to be negative if the insertion was negative, but it's closer to 0 than all of the other omega values. So it's like the algebraically smallest one. So it's negative, it's closer to 0 than the other omega k's. And this value for the 0 time constant, it's kind of bounded in between negative lambda 1 and 0. Like if you were to follow this graph this way, it's never going to be, this omega naught is never going to be less than lambda 1. So it's always bounded in between negative lambda 1 and 0. And it doesn't matter how many delayed neutron precursor groups you have. When you plot this function, it's going to look like this. You're just going to have more vertical lines depending on how many delayed neutron precursor groups you got. Um, and it doesn't matter how many precursor groups you have, you'll always see these exact same trends. You'll always see I of these time constants being negative, and then the other one is going to match the sign of the reactivity. And you'll also see that that the omega zero time constant is always bounded in between. If the reactivity insertion is negative, it's always bounded in between negative lambda one and so this is what we call the graphical solution of the n-hour equation, and it's how you can find what all of those time constants are. Um, and then because of the nature of our solution and the results of these time constants, we can understand and use this to kind of simplify our thinking. So these are like the interpretations that we want to be able to have for the n-hour equation and its solution, that I of those omega k's are always going to be negative. The other one is always the largest algebraically. It's always real. It always has the same sign as the reactivity insertion. If the insertion is negative, it's always bounded in between negative lambda 1, or what we can call lambda minimum, and 0. And that lambda min or lambda 1, it corresponds to the shortest lived delayed neutron precursors, or the ones with the should be shortest half-life. Um, anyway, I actually I need to double check that. I think that's a typo, but it is the smallest of the density. Yeah. Let me revise on that one. But either way, those minimum, the lambda minimum, the lambda ones, that's going to correspond to the group that has bromine 87 in it. Bromine 87 has a half-life of about 55 seconds. So the lambda minimum is going to correspond to that half-life. And we know that the relationship is that ln of 2 over the half-life. So the lambda min is going to be ln of 2 over that t1 half, which was 55 seconds. And if you do that calculation, I believe you get 1 over 80. Yeah. You get approximately 1 over 80 seconds to the minus 1. So that lambda minimum is important because it kind of tells you that 1 over 80 seconds is like the fastest our system could respond to a given change. Like if we have a negative reactivity insertion, what that actually tells us is that it would take at least 80 seconds for our system to be able to shut down. And so we can take these interpretations and we can learn a lot about how to study reactor behavior and the response of a reactor if you have a reactivity insertion that's either positive or negative or 0. So let's first consider that the reactor is made to be subcritical. So if we make the reactor subcritical, it means that we have a negative reactivity insertion. And if the reactivity insertion is negative, then all of the omegas, all of those time constants are going to be negative. So kind of going back to this picture here, if our reactivity insertion is negative, then all of these time constants are going to be negative, and omega 0 is going to be negative too, but it's going to be like the least negative of the time constants. So if we were to investigate how the system evolves at a large value of t, we've got a bunch of exponentials, right? Like our solution for n of t, it looks like e to the omega 1t plus e to the omega 0t, e to the omega 1t, and then we have a bunch of those all the way up to e to the omega 6t, because there were 7 of them in total. And so what we just said, though, was that all of the I terms, all of these omegas are going to be more negative than omega naught. So as time moves forward, what's going to happen to these exponentials relative to the omega 0 one? Which exponentials are going to die away first? The ones that have the more negative value of the time constant are going to die away first, right? Because like some of these, I don't know what the scale is here, but like maybe this is -10 and -5 and -4 and -3 and -2 and -1. So if we have e to the -10 times t, or e to the -5 times t, or e to the -2 times t, and then we let t go to a big number, then you're going to be doing e to a negative of a big number, which is going to exponentially go to zero. So the point of thinking about these time constants in this way is that in terms of which one dominates, it's always the omega zero solution that's going to dominate because it's the time constant that's going to be the algebraically smallest. So if the insertion was negative, it's going to be the last one to die away. And if the insertion is positive, then it's going to be the only one that's positive, and all of the others are going to die away as t goes to infinity. So basically what we're saying here is that when t is large, this is going to look like e to the omega naught, positive omega naught times time. In other words, the solution is going to be, oh shit. This is for a negative insertion. So we're just going to say of omega naught. Right, because omega naught was negative. I don't want to take absolute value because then it'll mess up that sign. So the solution is going to be dominated by the one with the algebraically largest time constant. All of the other ones are going to decay to zero as t is large. So in this system, in a subcritical system, then the neutron population is eventually going to decrease exponentially. And I guess actually, so omega naught is negative, but I'm going to make absolute value and put the minus sign in front just so that it's very clear that this is definitely going to decrease exponentially, right? If I just wrote e to the omega naught t, you might think it goes exponentially if you don't recognize that omega is negative. But in this case, the system, the population will eventually exponentially decrease. So we're saying the omega naught is going to dominate the behavior. And but we don't want to forget that all of those other omegas, all of those other time constants are in the solution. And if we were to talk about times like right after zero, those are going to be the ones that dominate what my solution looks like, but they're going to decay away really fast. So at the very start of the transient, you might have behavior that doesn't just look like exponential decrease because you're waiting for all of these other negative exponentials to like begin settling down. And as t gets bigger, all of those other exponentials are going to decay away, and then the solution is basically just going to be governed by the exponential, the time constant with the algebraically largest time constant. So that's what it's going to look like if we have exponential decrease. Um, and this is just kind of like reminding us about that lambda minimum, and that if we have a subcritical, if we have a negative reactivity insertion, that time constant is going to be bounded in between lambda 1 and 0. That lambda 1 corresponds to the lambda minimum, which is 1 over 80 seconds. So that means it takes about at least 80 seconds for the population to decrease by a factor of e. So if you have a negative reactivity insertion, 80 seconds is like the fastest you could possibly shut down. Um, but the population also in the early stages could decrease much faster than this 1 over 80 seconds because of all of those more negative exponentials being a part of the solution. Um, so now let's think about the supercritical case, which I think is a little bit easier to wrap our heads around. Because if we think about the subcritical case, a supercritical case, that's when our reactivity insertion is positive. So that's the top line. And notice that the I omegas are all negative except for omega zero. So if I let time be very large, what's going to happen to all of these omegas 6 through 1 as time gets bigger? Any solution that contains these omegas is going to go to zero, right? And the only one that's going to survive is the one that's positive. So like if we were to write this, it might be helpful to just say that like if we were to write this out, um, if we were to write out n of t, maybe it looks like e to the negative 10t, and e to the negative 5t, and e to the negative 4t, and then all of them are negative except for the last one, which is e to the positive omega naught t. So if my solution looks like this, and it does look like this, right? Because all of the time constants are negative except for the last one. So if I take this equation and then I evaluate it, or maybe I take the limit as t is a big number, then aren't all of these negative exponentials going to decay away as time moves forward? And if these are more negative than the omega naught one, they're going to decay faster than the omega naught one. So as time goes bigger and bigger, my solution is mostly just going to be dominated by the positive exponential because everything else is just going to decay to zero. So this is going to look like e to the omega naught times time. And omega naught is positive if my insertion is positive, and that means that the population, if this is what my behavior looks like, it says my population is going to eventually exponentially increase. Um, And it's a similar caveat with what we said before that this is making the argument as time is large, but right as the transient happens, all of these exponentials are still a part of my solution. And as a result, our behavior might not look like exponential increase in like the few moments after the transient, but as time gets bigger, this is the behavior that we would see. Yeah, yeah. So this one or the previous one? Yeah. Oh, sorry. Okay. Yeah. Um, and then last would be the critical reactor. So that means that the insertion is zero. All of our time constants are going to be negative, except for omega naught, which is going to be zero. So as we have a large t, all of the negative exponentials are going to decay away. The only one that's going to outlast is e to the zero. But e to the zero is just a constant. So this is just going to approach a constant because we're doing e to the zero. So if you have a critical reactor, then your population is just going to have a steady state. It's going to eventually reach steady state. Um, so that hopefully that makes sense that if you're critical, you are sustaining that chain reaction, so your population is at a steady state. Um, and again, it's a similar argument that if we made some reactivity change to make our system be negative, sorry, if we made some reactivity change to make our system have zero reactivity, those negative exponentials will be a part of the solution, and they will make it so that at the initial times of the transient, it might deviate from steady state, but if you wait for those exponentials to decay away, then eventually you're going to have a steady state solution. So this is a plot of what those point reactor kinetics solutions would look like for a reactor with no source. And when we write the point kinetics equations, we use n of t as like one of the variables. But and what you'll see when you do the more detailed point kinetics derivation on homework 5 is that that n of t can actually represent any amplitude function. So n of t in those point kinetics equations, you can replace n of t with like any integral property of the reactor. So you could replace n of t with it could be the number density of the neutrons. It could just be the number of neutrons. You could replace it with the flux. You could replace it with the power density or the fission power or the reactor power. You can let n of t be any integral quantity as long as you make the units be consistent for your definitions of the other terms. So it's very common to see the point kinetics equations with n of t substituted with the reactor power, which is p of t. But everything that we just talked about holds. And so the trends hold as well. And so this is showing what our system would look like if we had a very large positive reactivity insertion. So if we have a very large positive reactivity insertion, the system just immediately kind of like blows up to infinity. And that's what's being shown here. If we have a reactivity insertion that is positive but not incredibly large, then we have basically an initial jump followed by exponential increase of our power, which is what we would expect for a positive reactivity insertion, that system is eventually going to increase exponentially because we only have one positive time constant. All of the other time constants are negative. So as we let t move forward, those negative time constants are decaying away, and we're just left with a solution that looks like the positive exponential. And then this black line down here is showing a negative reactivity insertion. So right as the transient happens, you get kind of like a prompt drop in the power. And then you get an exponential decrease of the power because of what we were just talking about, how all of our solutions, all of the terms are, all of our time constants are negative, so we get exponential decay. And so that's what our behavior looks like in a long time, over a long time, is an exponential decrease in the power. So the point kinetics equations and the n-hour equation give us a really powerful tool by which we can say, if I have a reactivity insertion, is it positive or is it negative? How is my system going to behave in response? So that's the main point, and that's what we want to be able to get out of these equations. I think I'm going to stop from there. When we come back next time, I'm going to talk a little bit more about these transients, about these transient plots. I'm going to talk about feedback, the reactor feedback concept, um, and that'll be what we talk about next time. Question?
You go back to your delete solution form slide. Wow.
Alan? If y'all don't have any questions, have a good one. If y'all have questions, let me know. I'll stay for a little bit. And if not, take care and I'll see y'all on Thursday.